Kylo Limit Loren, talking to you about the intermediate value theorem. Why was R2-D2 so angry? Because people kept pushing his buttons!
So the first thing we're going to talk about is the intermediate value theorem that says if f is continuous on the closed interval AB, where f of a is not equal to f of b and k is any number between f of a and f of b, then there is at least one number c in the closed interval AB such that f of c is equal to k. So this looks a little bit confusing. Let's look at this graph down here and it'll help you understand what this is saying. So it's saying if f is continuous on the closed interval AB. So we have our interval AB and we have a continuous function here, f. Now we're saying that f of a is not equal to f of b. So the two endpoints have different y values. That's what that is saying. So we have a continuous function on our closed interval AB, closed interval because the two endpoints are not wholes. And we have f of a not equal to f of b. So the two endpoints have different y values. And k is any number between f of a and f of b. So k is a y value that is between f of a and f of b. Then the intermediate value theorem says that there exists at least one number c in the interval AB, so one x value, we'll call it c, that is on the interval AB, such that f of c is equal to k. So that when we plug in c to our function, we get a y value equal to k. So again, we have a continuous function, we have endpoints with two different y values, and we have k, some y value between f of a and f of b, the two different y values. Then there must exist, by the intermediate value theorem, some x value c, where if you were to plug it into the function, you would get a y value of k, that y value between f of a and f of b.
No, I am your father. Example time.
Now example 1 says verify that the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by the theorem. So the first thing we're going to do is say, is f continuous on the closed interval 0 to 3? Because that's the interval we're working with. In order to figure that out, you just look at the function and you say, are there any asymptotes or holes for this particular function? No, there's not. This is a parabola, so we can say, yes, the function is continuous on the closed interval 0 to 3. Given the interval 0 to 3, we want to find the two y values of our endpoints, f of 0 and f of 3. So let's find the two y values of our endpoints. We plug 0 into the function for x, simplify, and we end up getting f of 0 is equal to 8. So our first endpoint has a y value of 8. Our second endpoint, f of 3, if we were to plug in 3 to the function for x, we would get a y value of -1. So our y values for our endpoints are 8 and -1. We then ask ourselves, is f of c between f of 0 and f of 3? Is our y value that we've chosen, our k value that we talked about earlier, is that between the two y values of our endpoints? Well, f of c is equal to 0, and because of that, 0, you can see, is between -1 and 8. Therefore, f of 3 is less than f of c, which is less than f of 0. Therefore, IVT applies. We can apply the intermediate value theorem to this problem. Next, in the problem it says, find the value of c guaranteed by the theorem. So, in order to do that, what we're going to do is take f of c, which is 0, and set it equal to our function, f of x. So we need to figure out what values of x would cause this function to equal 0, to give us that y value. So we set them equal to each other, and now we solve for x. Well, here, there's no way to just solve for x, right? This is a quadratic trinomial, which we know we solve for by factoring. And if we were to factor x squared minus 6x plus 8, we get x minus 4, the quantity, times x minus 2. So because we know both of these things multiply together to make 0, we set both of them equal to 0 and solve for x. So here, x is equal to 4 and x is equal to 2. But we look back at the original problem and we see that our closed interval was from 0 to 3. 4 is not on that interval, right? We're looking for an x value, c, that is on the interval 0 to 3 that would give us the y value of 0. And since 4 is not on that interval, we cancel that out and we see that our c value that we're looking for is actually 2. We then look at our graph and you can see that our interval from 0 to 3 would be right here, and on that interval we have a y value of 0 at x is equal to 2. So that confirms our answer.
A long, long time ago in a galaxy far, far away. Utah!
So we're doing the same thing here. First, we want to verify that the intermediate value theorem applies to the indicated interval. So the first thing we need to do is figure out, is our function continuous on this closed interval? If it's not continuous, if there's a hole or an asymptote on this interval, you can just automatically say the intermediate value theorem does not apply because the function is not continuous. But since we have a cubic function that has no holes or asymptotes, we can say yes, our function is continuous on this interval, and we can move on. Next, we need to find the two y values associated with our endpoints. So what we do is we take each of those endpoints and plug them into our function to get the y values associated with them. So if I were to plug in -2, our first x value of our endpoint, into the function, I get a y value of -25. If I plug in 4 to the function, our other endpoint, I end up getting 18 as the y value associated with that. Now I determine, is f of c between f of -2 and f of 4? So is our given y value that we're looking at 1 between the two y values associated with our endpoints, -25 and 18? And the answer is yes, 1 is between -5 and 18. Therefore, f of -2 is less than f of c, which is less than f of 4. So we can use the intermediate value theorem. We have a y value that is between the two y values of our endpoints. Next, we want to find the value of c, our x value, that would make the function have this particular y value, 1. So what we do is we take 1 and set it equal to our particular function, x cubed minus 3x squared plus x minus 2. What we can do then is solve this by setting one side equal to 0. We can then factor by grouping here. If I were to factor out an x squared here and factor out a 1 here, I could then rearrange this and write it as x minus 3 times the quantity x squared plus 1. That's how you factor by grouping. If you don't remember how to do that, make sure you look up a video tutorial on how to do that. That was Algebra 1. Next, what we do is we can set each of these equal to 0 and solve for x. So I say x minus 3 is equal to 0 and x squared plus 1 is equal to 0 by the zero product property. Here, I add 3 to both sides, I get x is equal to 3. Here, if I were to subtract 1 on both sides and square root both sides, I would get x is equal to an imaginary number, so we don't even look at that. So we have x is equal to 3. Is that on our interval? Yes, our interval is from -2 to 4, so we have found our c value of 3. We confirm this with our graphing calculator, and you can see that at x is equal to 3, somewhere over here, we're going to have a y value equal to 1. Now example 2 says prove that the function below has a root between -3 and 0. So this example is a little different than the previous example because we aren't flat out given a closed interval and an f of c value. But if you read the question a little closely, you can see that we are actually given those things. We want to prove that the function has a root, meaning that y is equal to 0, meaning that we have an f of c equal to 0 at some point on the interval from -3 to 0. So we have a closed interval, we have an f of c value 0. All we have to do now is verify that we can use the intermediate value theorem. In order to verify that, we first ask, is f continuous on the closed interval from -3 to 0? Because if f is not continuous, if there's an asymptote or hole on this interval, we just automatically say the intermediate value theorem cannot be applied. But here we have a quadratic function. There are no asymptotes or holes, so we say yes, the function f is continuous on this interval. Next, we have to find the y values associated with our two endpoints. So we take each of those endpoints, plug them into our function, and get the y value associated with those. So when I plug in our first endpoint to our function, I end up getting a y value of 16. When I plug in the other endpoint, I get a y value of -5. Now we're trying to prove that the function has a root between -3 and 0, meaning that y equals 0 at some point on this interval. So if we look at the two y values that go with our endpoints, you can see that they are 16 and -5. So is 0 between 16 and -5? And the answer would be yes. Therefore, by the intermediate value theorem, there must exist some number c, some x value, between -3 and 0, such that f of c is equal to 0. You have a root on this interval. And we confirm this with a graphing calculator. If we were to graph this particular function, you can see on the interval from -3 to 0, we do have a root.
I killed my dad. You try.
Okay, so this says prove there exists some real number p in the closed interval from 0 to pi such that 2 cosine of p is equal to 1. Now this might look a little different, but it's the same as the previous example. Instead of c, we're using p. Our closed interval is from 0 to pi. Our function is 2 cosine of p, and our f of c value is 1. We're just trying to find whether or not there exists some x value, p, on this interval, where if you were to plug that number in for p, you would get a y value of 1 for this particular function. So in order to do that, we're going to use the intermediate value theorem. And the first question we ask when determining whether or not we can use the intermediate value theorem is our particular function continuous on the given interval? Well, the cosine function has no asymptotes or holes. Therefore, yes, our function is continuous on our given interval. Next, what we need to do is plug in each of the endpoints to our particular function to get the y values associated with those. So if I were to plug in each of these endpoints for x in our particular function, I would get the y value associated with those endpoints. Now they are different, so that's good for the intermediate value theorem. We then ask, is f equal to 1? Is that between f of 0 and f of pi? So is our f of c value 1? Is that between 2 and negative 2? Yes, it is. Because this y value that we're looking for is between the two y values of our endpoints, we can say that the intermediate value theorem applies. So therefore, by the intermediate value theorem, there must exist some number p between 0 and pi such that f of p is equal to 1. There must be some x value, and we're calling it p, on this given interval that would cause this function to equal 1. And you look at the graph and you can see, yes, we confirm our results. Between 0 and pi, we have a y value equal to 1. Now example 3 says let f of x and g of x be continuous on the closed interval ab. If f of a is greater than g of a and f of b is less than g of b, prove there exists k between a and b such that f of k is equal to g of k. So here's what's happening. We have two separate functions, f of x and g of x, and we have our closed interval ab. So if we were to plug in a to each of the functions for x, this would be a greater y value than this. If we were to plug in b for each of the x values, this would be a lesser y value than this. So we are just trying to prove that these two functions cross at some x value, which makes sense because if one starts greater and then becomes the lesser function, they have to cross at some point. So here's how we do this. What we do is we say h of x is going to equal f of x minus g of x. And you say, well, why would we do that? Because if we create some new function h of x that's equal to f of x minus g of x, all we have to do is show that at some point h of x is equal to 0. If we can prove that h of x equals 0 at some value k on this interval, then we can prove that f of k is equal to g of k, because in order to equal 0, these must be the same. So we let h of x equal f of x minus g of x. We then ask ourselves, is h continuous on this closed interval? Because these are both continuous functions, as it says here, then the difference of two continuous functions would be a continuous function. Next, we figure out h of a and h of b. Well, we can't actually find out a number, but we can figure out whether or not they're greater or less than 0. So let's look at this. H of x is equal to f of x minus g of x. If I were to plug in a, I would get h of a is equal to f of a minus g of a. And we look up here, f of a is greater than g of a, meaning that if we subtract these two values, we get a positive number. You then plug in b to your new function up here, and you get f of b minus g of b. Now you see up here that f of b is actually less than g of b. So if you do a lesser number minus a greater number, you're going to create a negative number. So f of b minus g of b is negative, therefore h of b is less than 0. So since we have over here h of a is greater than 0 and h of b is less than 0, we then ask, does h equal 0 between h of a and h of b? Yes, it must, right? Because if h of a, the beginning of our interval, is greater than 0, some positive number, and h of b is less than 0, some negative number, that means at some point it must cross the x-axis. So we say that, yes, h must equal 0 at some point between h of a and h of b, meaning that f of x and g of x must be equal at some point on this interval. So we can say by the intermediate value theorem, there must exist some number k between a and b such that h of k equals 0. And since h of k is equal to f of k minus g of k, and that equals 0, then f of k must equal g of k.